Easy. Today I want to talk about two things. First, I want to finish the discussion of gossip by explaining topology management, which I started last week. I made the slides much better. I think the slides last week were not very good, so the slides are much better. So I hope this explanation will be much easier to understand. This is a real gossip algorithm, high strength, used in industry, bringing order out of chaos. So gossip is the main thing that brings system up from randomness into some kind of an ordered structure. And this is a really good example. And the second part will be content distribution. And I'll explain how BitTorrent, which is one of the most famous ones, and today this is still a very important kind of algorithm. It's also an example of a peer-to-peer algorithm, like gossip. It's similar to gossip, except there's a new thing. It's not just an algorithm with nodes running nice code. It has selfish nodes. Nodes that are only out for their own profit. And so how do you get the whole algorithm to work? As soon as a selfish node has enough, it stops. And you have to give incentives. This is the really new thing in BitTorrent. This is something that we have not seen yet in any algorithm, where you have to take some kind of economic concept, self-interested nodes, where it's actually the human user behind the node is selfish, and in order for BitTorrent to work, you have to give incentives. You have to make it in their interest to keep being part of the system. So this is very similar to gossip. You also have peers and information being exchanged and so on. So this is kind of like gossip, but with this new idea. Okay? So basically today we're seeing two really kind of sophisticated forms of gossip that are really, really used. And this BitTorrent algorithm, very popular, of course. Okay, so let me start. First, a few seconds of respect for the Ukrainians who are doing very well in fighting for their freedom and for our freedom. Okay? So, topology management. Topology means you have a network where all the structure is known. Okay? And if you have a bunch of random nodes, well, how do you have no structure? They're just random neighbors. You can try to order them. And topology management, you can make a service that provides that. And the algorithm I'm going to show you is called TMAN, Topology Management. This is a famous algorithm that caused a lot of work, and many real systems are doing things related to that. And there's also a paper in the Moodle on TMAN, which explains a little bit more better maybe than the slides. So it's based on a ranking function, so you basically can calculate distances between nodes, okay? But that's all you know. For any random node, you know the distance. But the random node might be far away, even if you want it to be close, okay? So with this function, you can build structures, rings, a Taurus, which is like an inner tube, binary trees, okay? And the gossip cycles will cause this topology to appear, okay? And gossip with this algorithm is useful for large distributed systems, okay? And other protocols can be jump-started. That means if you need some kind of structure between the nodes, you want to do replication and you just have random nodes, but you want some kind of a nice structure, a ring, for example, but you just have random neighbors. You can use this algorithm to build that structure. So gossip is really the first thing that is between order and chaos, okay? Between random systems that you don't know anything, it's random, and some really nice ordered system doing what you want, gossip can do it, okay? So, topology management, how does it work? And we have a specific formal definition. There's many ways. So you have a set of n nodes, which can be very large. Each node has a view of size c, basically much smaller, maybe 100. It can see 100 nodes out of 1,000,000. Okay, and it has no descriptors. So the address, like IP address, whatever, profile, something used to calculate the node distance. Okay, so if you know that, you can actually calculate distances. But that's not enough to have order, huh? It's not because you can calculate the distance between two random nodes. There might be no path between them. Okay, so that's only the first step. So you know the distances. And you are given this. You're given one function, r, which is called a ranking function, between any node x and a set of nodes, y. It basically orders them. So basically, it's giving you a little bit better way of looking at it than distance. Basically, the real information is you have distance between nodes. So if I have the ranking function, I have a ranking between x and some nodes y1 to yn. It gives me a set of lists or orders. So something like this. So here's one ordered list, and it's ordered in terms of increasing distance. So A is closer to x than yb and yc, and they keep getting farther and farther. Okay, or according to some distance function, so you have some distance function. That's all basically you have. But with this ranking function, you can make the gossip algorithm. Okay? So that's what you're given. A set of all orderings. Okay? You never really need to construct this set, but this is what you need to do. So this problem is this. I want to do something for every node. So I'm building a topology. So every node has to be in the right place in the topology. Okay? So for every node, I want to find the closest neighbors, and according to ranking x. Okay? So basically, something like this. So if I have all nodes except x, so I have the ranking of x compared to all the other nodes. It's something like this. And here I have some kind of partly. This is the closest nodes to x. Okay? Of course, it's the first one. And the view of x has to be, this has to be the set of nodes that are closest to x. That means for every node x, I want to find the nodes, the small set of nodes, view, which is size c, that are closest to x. And once I have that, I have the topology, yeah? So for example, if I want to do a square, if I have 4 nodes here, the 4 closest ones, then I know what the topology is, So with this ranking, I can make an algorithm. Okay? So that's the definition. And then the algorithm is this. So as usual for gossip, the algorithm is not complicated, and there's 2 parts. An active thread and a passive thread. Okay, so the active thread will initiate communication. So it finds some node, a peer. How does it find it? Well, it does something called peer selection, which we'll explain. It finds a peer, okay, and it basically has this view its local view together with the peer. It sends that to the peer, and then it receives the peer. So there's an exchange. This is but what you're exchanging is the view. So the view is the 100 closest nodes that you know right now. Maybe they're not really the ultimate 100 closest, but it's as best you know for now. Okay? So then you have 200. You have your own view, and you have the one you get from P, and then you merge them. Okay? In some way. But basically, you're going to pick the closest ones. So you have 200 nodes. You have 100, I get 100. And out of these 200, I pick the 100 closest. That's pretty straightforward. So here I'm writing it very generally, but basically it's very straightforward. So maybe the extra 100 nodes, there's some nodes there that are closer than the 100 I know, and then I take those. Okay? And the passive is just doing the opposite sign. It receives, so it waits for a message, as infinite loop. It gets the node and the view. Okay, it has its own view, which is view here. View Q is the view coming from the other one. It sends its view to the other one, and again it will pick the one that's closest to it. So both of them are going to get some advantage. Okay, so that's it. That's the algorithm. And then you have some functions. Initial view, merge, select peer, and select view. And you have to pick them kind of right. So initial view is just some random nodes. Okay. Select peer. Select peer, you have to pick one. But it's not good to pick the closest one. Okay. You have to pick one that's kind of close because you want to improve the topology, but not one that's too close, so you won't really improve. So what you're going to do is pick a random sample from the first half of the view, randomly. So from the half of the nodes that are the closest ones to you, you pick randomly. So it's not exactly the closest one, but it's not going to be the farthest one. It's one that's a little bit close. Okay. Merge is just union. And select view here. So buffer is the union of these two. So it will have 200 nodes, if C is 100. So you rank all of them, these 200, and you return the 100 smallest ones. You can see, the ranking lets you order them and know which ones are closest. Okay? You pick the 100 closest, and that's it. So basically, you have 100 nodes, you find 100 somewhere else, then you have 200, and you pick the 100 closest. Okay? So that's not very complicated, you see. And you see that eventually, it's kind of going to be kind of exponential. The more steps you do, the more nodes you're going to be touching and combining. Okay? So some ranking functions. So basically, what you need to know is the distance. So here's just some simple example. Line. A line is going from 0 to n minus 1. And the distance is so A and B are the numbers. And the distance is just the absolute value of the difference. If I have a ring is like a line where the two ends are connected together. And so the distance is a little bit different. It's the absolute value of A minus B, but it's also the other side, n minus the absolute value. So this one, but also the other one. And you pick the smallest one. Then you have mesh and torus, typical example. So a mesh is just a square with two-dimensional grid on it. And they're all numbered. So you have some coordinates ij here. 0 and minus 1. And the mesh, and it's just a Manhattan distance, which is going either left, right, up, down. And then the torus is the same as a mesh when you combine the opposite side. You combine these and you combine these. So combining these gives you like a tube, and then you combine them and it gives you like an inner tube. Huh? So it's kind of similar idea as the line in the ring, huh? Or the line you combine. So just some examples. Another nice one is binary tree. Okay, so you have nodes that are organized like this. You have some roots, and you have sub-nodes and so on. Okay, and the ranking is how many, according to how many steps you have to do. So, for example, to go from this node to this node, I have to go up one, and down one. So the distance is 3. Okay, so you rank like that. So that's just some examples. Okay, and here's an example of the algorithm working on a torus. I showed it briefly last week, but this week we're going to go more in detail. So I have each node starts out with random nodes, so it's a mess. So 0 cycles, which is not shown, is just some random graph. There's nothing, just a random graph. After 3 cycles, it looks better. The nodes, some of the nodes are connected to the right neighbors. So 1 cycle is n view updates. Okay? That means each time t, a node will do in the loop, it will do 1 round trip. And because all nodes are doing it and each round trip has 2 of them, the cycle will be t over 2 time units. Okay. Here we have an example for a 50 by 50 mesh, which makes a torus of 2,500 nodes. And it starts by a uniform random graph, and the number of neighbors in the view is 20. Okay? And I'm not showing all the neighbors here, I'm only showing 4 out of the 20. So here for each node I would have to show 20, but I'm only showing the forest closest one. The other ones is a mess, okay? But eventually we have a really beautiful torus where each node is connected to perfect 4 other nodes, okay? After 15 cycles. But how do we actually get to that? It's not that simple. It's a little bit, there's a few subtleties, okay? And because the algorithm has 2 parts. So the first part is what I showed you. You take 100 or 100 nodes, you pick the 100 closest. So you keep repeating that. After 1 cycle, you get the closest C out of 2C. But since then you do more, each time you double it basically. After I cycles, the view will be the closest C nodes out of 2 to the I times C. So you can see you're looking wider and wider. And that's the first part of the algorithm. That's called rapid convergence. But we'll see it's not enough. Because when at the end, when there's only a few nodes that are wrong, this doesn't really work so well anymore, and we have to change it. So we had to actually organize the algorithm in 2 phases. Rapid convergence and endgame. Okay? And we'll see also that there's endgames in the content distributions. Very often you have this notion of the normal working and the endgame. Okay? So the rapid convergence, we want it to work well. There's actually a source of error, so we have to slightly optimize, and it's called balance. And I'll show you the performance with and without balance, okay? So if we just do this naively like this, the code that I showed you, it's actually unbalanced. And the idea is the following. So each node will pick a random node and do exchange, right? But that's random. Okay? So what if one node gets picked a lot? If one node, by the randomness, has a lot more communication, it will have more information and it will converge faster, okay? Because randomly, many other nodes have chosen it, okay? So that node will have actually a better topology than the others. But if a node is by randomness not picked so much, it has slow convergence and it will not have good information. So if both of those are bad, if the node is already really converged, then there's not so much randomness there anymore. And if some other node wants a random view, it won't really get it. It'll get some converged view, so that's less useful. And the other direction is the same, because the nodes are doing it symmetrically. So a node that does not get chosen communicates too little. It has a very bad view, but the other node maybe has a better view, but picking this really random thing doesn't really help. It needs to pick something a little bit less random. So basically all the nodes should converge at about the same speed, okay? And that's balanced. And so the naive algorithm, the one I showed you, the code I showed you, is actually the unbalanced algorithm. So you need to do a little tweak to make it balanced, and I'll show you. It's actually very easy to make it balanced. Okay? So we can analyze this. So this is kind of a not very complicated analysis. So let's look at the node A. Eventually, there's going to be some adjacent node. So some node is going to be right next to it, the closest one. So if it's a line, there's these two guys. If it's a mesh, there's four of them. If it's binary tree, it depends. If A1 is the root, it has two closest nodes. If it's a leaf, it has one. And if it's a middle node, it has three. Okay? So eventually, which after a certain number of cycles, the adjacent node B, which is like this one or this one, it has to be in the view of A. Okay? That's reasonable. Well, we have to converge. Okay? Now, just define the maximal rank of the adjacent node with respect to the base node. That means how many close ones are there. So here I have four close guys. That means the rank of this one is 1, but the others, they have to be in some order. So maybe 1, 2, 3, 4. So the maximum rank is 4. Okay? For a binary tree, it's either 2, 3, or 1. Okay, this is not so important, this maximal rank, but it lets us do a simple calculation. Okay? Define the probability that adjacent node B is in the view of A after cycle I, after a certain number of cycles. So eventually it has to be there. How long is that going to take? Well, after one cycle, 0 cycles, I have C random nodes, and there's N, or N minus 1, because I'm not counting myself. So this probability is very low. So maybe B is already there from the beginning. Okay, that's low probability. Now, if this maximal rank is less than C, that means I'm always going to pick it in the choice. From C to C, you pick the closest one. So that's the only reason why I need to know it. Then when I do one more cycle, I'm looking at 2 times as many nodes. So it's 2 times this. PABI is 2 PABI minus 1. So it's 2 to the I, PAB 0. So each time I do a step, I'm looking at twice as more and many nodes, and the probability that the adjacent one would be, in my view, doubles. Okay? So this probability, let's just call it P, is C times 2 to the I divided by n minus 1. So I put in C over n minus 1, this. And this one will eventually get to 1. So it will get close to 1. So when this one is less than 1, then we can compute I. C times 2 to the I over n minus 1 is less than 1. We multiply, we take the logarithm. And I has to be less than the logarithm of n minus 1 minus the logarithm of C. Okay? So once we get close to this value, we basically have expanded to cover everything. And then they simulated it. So Baboglu and Giulasoli simulated this, okay, for a bunch of topologies. And here's two graphs coming from the paper. So here I have the number of cycles. So a cycle, each time all the nodes do a round trip. 0 cycle, 1, 2. And here we have n is 2 to the 17. Okay, so that's 1,000 times 128. It's like 128,000. And c is equal to 40. Okay. And if you compute the I, it tells you that eventually the I is going to be 12 cycles. So the logarithm of this minus the logarithm of 40, gives me 12. So here is the number of nodes I'm touching more and more. Eventually it kind of saturates because I touch all the nodes and I start to repeat. So this graph is going to slowly go to 1. It's the proportion of nodes that I'm touching. And you see 12 is like the part where it changes. And this is for different topologies, okay? And I'm showing you with balancing and with no balancing. So I'll explain how you do balancing. But so you have this one, it still converges well, even with balancing or no balancing. There's one that's a little bit worse than the others. And here is the convergence factor. I said every cycle I do 2 times more, okay? 2 times. But it's not exactly 2. So here's the number of cycles. Here's 2. And after 12, I reach everything, okay? So here's like the ideal. I want to get 2. But I'm not going to actually touch exactly twice as many more. But it's sort of. You see, it kind of stays near 2. It eventually goes down when I get near 12 cycles because I'm kind of saturating out. I'm touching all the nodes. Okay? So you can see this simulation of the algorithm. Okay, I'll explain how you do balancing. Here you do with and without balancing. Okay, so the rapid convergence phase, what I just showed you, is converging exponentially. Yeah? Every step, it's like doubling. But you can do better if you balance it. If you make all the nodes converge at the same rate, because now some of them are going to be converging very fast and some of them are really slow. So that's actually very easy. Each node counts. It counts the cycle number and it counts how many times they have been contacted. And if this number is greater than the cycle count, it refuses any connections. That means if I'm in cycle 10 and the node has already received 25, or we won't with this, but let's say it has received already 10, it will not get, the 11th one will not be accepted. So the receiving node refuses contact if I already have had enough, okay? The same as the cycle count. So the sending node, when I pick a node randomly, the node at the other end might refuse. That means I actually have to search for a node. I do like a ping message. Will you accept me? And it says yes or no. Will you accept me? Until it finds one. So these are like ping messages. And eventually it finds one that does not have 10, has 8 or 9, and then okay, then it's good. And with this trick, they're all going to be converging at about the same rate. And actually the algorithm goes a lot faster if you do that. Okay? Simple optimization, and we'll see with the graphs, makes it go a lot faster. Okay, so that's the rapid convergence phase, but you can't do that completely to the end. At the very end, you have some left behind nodes. So let me explain now what happens at the end. So you're building a torus. Okay, go double in each step, and eventually you almost have a torus. And there's a few nodes that are not right, in the right place. A few left behind nodes. And you want to put them in the right place. But the random selection is not really the right way to put them in the right place, huh? So, for example, if I have a mesh, here's a mesh, and here I have a node, and here I have a node, and this one is empty, but I have a node here, connected here, and this one should be there. Okay, it should be this guy's neighbor, but it's not. So somehow I have to get this one to fill the gap here. Because the distance is actually, it shows that it should be there. But doing random selection is not really very efficient for that. Okay? So you have these stragglers, these leftover nodes, a few, small number, that are not in the right place. And you keep running, and eventually they get a little bit closer and closer. But how do they move? They can only move according to the topology, okay? So this guy is going to talk to the neighbors, so it's going to talk to these guys. So maybe eventually this guy is going to move to here, and then it'll move to here, and eventually it gets where it has to be, step by step. But it's moving on the topology. So it's actually kind of routing these straggler nodes. Huh? And the ring is the worst, huh? Because the ring is a really linear thing. If I'm on node 50, and there's a node at position 10,000 that has to be 51, it's going to take a long time to get there. Okay? So instead of random selection, we actually do something which is like routing. We pick the one that's closest on the topology. We kind of do routing instead of picking nodes at random. Okay? So we change the select peer, not to pick random nodes, but to favor the ones that are close by so that it does routing. Okay? So this is what you get done when you do this. So here's all four possibilities. Okay, here we have a ring with 2 to the 17 nodes. That's 130,000 or something. And C is equal to 40. Okay, the diagram is averages of 20 runs. And here you have the cycles. And here you have the number of nodes that are not good, that are badly placed on the ring. Okay? Eventually it gets to 0. You can see, so this is logarithmic graph. You can see the best one is doing balancing and routing. And at the end, after 29 cycles, it's perfect. So getting rid of that last one seems to take time. Right? You see this last one here? So at the very end, you have kind of step function. When I have 4 nodes that are wrong out of 100,000, huh? And eventually I have 3 nodes that are wrong, and 2 nodes that are wrong. 1 node is wrong, and then I'm done. So this last piece takes time, huh? To get those last guys in there. And this graph gives you the 4 possibilities. So the top one is when you have no optimization, no balancing, no routing. The second one is if you have no balancing, but you start the routing from the beginning, so that's already better. The third one is if you have balancing but no end game, so at the very end it takes a long time. And here you have both the balancing and the routing. That means the convergence is faster, but also the end game is much shorter, right? Instead of this very long end game. So this one is taking like 20 cycles or something, huh? Here it's only taking a few cycles, huh? So the best is you do both balancing and routing, okay? So this is for the ring, where it's actually the worst, huh? So shows you that both balancing and routing optimizations are essential. But if you do both of those, then the T-man is a very practical algorithm, and it gives you a perfect topology, okay? perfect one. And so conclusion, so T-man is very general. It works for any kind of topology. It converges quickly. It scales. So the simulations were done up to 1 million nodes. So then it works. And it's robust, okay, as gossip is. And you see how it works, gossip, but it actually works in 2 phases. So it's not that we invented the 2 phases, it's that the algorithm naturally has 2 phases. The rapid convergence when everything is random and everything is good, and an endgame when there's only a few mistakes, so you have to be smarter. And we give 2 optimizations that make it go better in both the rapid convergence and endgame. Okay? And algorithms similar to T-man are used to bootstrap distributed systems, especially large systems. Systems like distributed databases, okay, are using algorithms like this, or overlay networks, what's called distributed hash tables, will use algorithms like this to create order out of chaos. So that's a very interesting concept. Philosophically, this is a very interesting kind of algorithm, creating order out of chaos. Okay, and there's some more graphs that I can show you to show the convergence time. Here you have the number of bad links, so missing links. So you have to go to 0. And here it's with binary tree, ring, and Taurus. Okay. So the ring is kind of the hardest one. That's reasonable, because it's linear convergence. The Taurus is better, but it's n square root of n convergence. And the binary tree is kind of doing the best. And you can see that the high sizes of views helps a lot. So all the thick lines are big views, which are doing very well. The thin lines are small views, so that doesn't do so well. So you see that having big views is a good idea. Okay. Here you can see the convergence rate. It's funny that it's actually a little bit higher than 2 in the beginning. When things are very, very random, then almost anything is good, But at the end, it goes down, of course, Okay, let me just now give you another example of gossip, which is coming from biology, and showing that gossip is actually very general, even in nature, that this is used, okay? This is called heartbeat synchronization. Natural organisms, you can see sometimes different pieces that somehow synchronize with each other, even if they can't really see each other. They only have neighbors. So heart pacemaker cells. So in your heart, you have these cells managing the beats, but each cell can only talk to its neighbors. Chirping crickets, where each cricket can only hear the close ones. Menstrual cycles, when you have, for example, women that are together in the army or something, that synchronize. Fireflies that synchronize. Whenever there's a cycle, it tends to synchronize. And they're all cases of coupled oscillator model. Each actor is an oscillator, like a pendulum. Firefly will give a light and then later give another light. So it oscillates. And all these oscillators are independent. Okay? But they're somehow connected together. Maybe the fireflies can see a few neighbors, visual clues. Maybe the crickets, there's mechanical vibrations. In machines, you can have that too. Or they can smell things. So the oscillators can sort of see neighbors. You see, it's kind of like gossip. Each node has some neighbors. Okay? So certain species of male fireflies, Luciola pupilla, will synchronize. and they're, for example, in trees. And a long time, nobody believed it, okay? People went to the tropics and said, yeah, I see trees where it's all flashing at the same time. And the people say, no way, you've been drinking too much punch over there or something. No, it's not true. Yes, it is true, but there was no video, so you couldn't really prove it. But now we know it's completely true. So each firefly has a small set of neighbors. The communication is not instantaneous. So each firefly sees the neighbor and then takes some time, reacts. Each firefly has a local clock, okay, with some period that's random, and with some phase also. So this is push. The information is pushed out. Each firefly sees the neighbors but doesn't send anything back. The local state, we can say it's the phase of the oscillator. Okay? It starts at 0 going to 360 degrees, 0 again. But you can be anywhere in that period. Select P here is just the random neighbors, the ones that are close. And the update, well, depending on the arrival flashes, you will reset your local oscillator phase. So maybe you see flashes, which are phase 0, and then you will reset yourself to some fixed phase, maybe 0. And this has been measured, okay? So here you have time. So this time I think is going to be in microseconds. This is in seconds. Here you have the periods. So it starts out, they're very different, but this is not going from 0 up, from 850,000 to 1,150,000, and eventually they all converge. So this is actually really a thing, okay? So the Gossett model actually explains this coupled oscillator of the fireflies. Okay, that's the end of our discussion of gossip. So you can see gossip is a really important kind of algorithm, very different from the algorithms we saw in the beginning. Now I want to show another kind of gossip algorithm, which is used for content distribution. Okay, and the algorithm I want to talk about is BitTorrent. And content distribution is another problem. You have a file, like a movie, and you want to give it to lots of people, and all these people are connected in weird ways on the internet. They have friends and so on. And each person knows a few friends. So random peers, sort of. And so how do you arrange that? And the different thing between regular gossip and this is that each of the nodes here is an independent agent who decides whether they want to be part of the algorithm or not. In the previous ones, all the nodes were working together. They didn't have any independent will, okay? Here, the nodes have independent will, and they can decide to leave or to come in during the algorithms that it's running. And they get something out of the algorithm, which is the movie, but they also give something. They will send pieces of movie to other nodes, but that's expensive. So how do you get those nodes to stay in long enough so that everybody helps? So somehow you have this local incentive for global operation thing. And that's the big difference between an algorithm like BitTorrent and T-Man or the other gossip algorithms. Okay. So I'm going to show that. Okay. But let me maybe make a break now, and then we'll talk about content distribution after, and I'll show you the algorithm. Content distribution. This is a really important problem, and the algorithm that has huge success on this was an algorithm called BitTorrent, and even today, years after, so this is in 2007, and BitTorrent was invented around 2005. the algorithms are all evolutions of BitTorrent, okay? So the basic ideas are the same. So what is the problem? I have a whole bunch of users, thousands, millions, and I have content, a movie, a song, or something, okay? And on one server. How do I send this content to everybody as fast as possible? Now this guy has limited bandwidth, okay? So you can't just send one by one. We'll see, it's not very efficient, okay? Okay, fine. There's an easy solution. Throw money at the problem, okay? Millions. You buy bandwidth, you rent many servers, you replicate the content, and you send to everybody, okay? And that kind of works. There are companies that do content distribution that have huge number of servers. Akamai is in 2007, they were the world leader in content distribution. So they're still big guys, but there's many companies doing content distribution, Cloudflare, Fastly, Image Engine, Amazon CDN, Amazon Cloud, etc., etc. There's a whole pile of them. Companies. But you have to pay those guys. But maybe I'm just a poor person sitting at home, and I don't want to pay them. And let's see how we can do that. The idea is that instead of having a huge infrastructure, we use the bandwidth of the customers. And even Linux distributions will do that when they distribute their upgrades, okay, like Fedora. So here's an example. Let me give you an example of this to make it very concrete. Now this is 2007, so you basically multiply all these numbers by 1,000, okay, and it will still be valid. So here you have a user with download bandwidth 256 kilobits per second, upload 256 kilobits. Okay, nowadays people have a little bit more, so personally I have 400 megabits at home, so like a little bit more than 1,000, but basically a similar idea. And here I have a big server with a bigger bandwidth, 1 megabit per second. Okay? So each user has like a fixed one. So with this guy, you can actually send to 4. Or maybe this one number is not always so high, it can be even less, huh? But assume it's, if this is 256, you can send it to 4 guys. You divide this bandwidth equally. That's reasonable, right? So here, for example, I have a 1 gigabyte file, 2 CDs. That's very quaint, huh? Now I would have a high quality 16 gigabyte movie, and I have the server, 1 gigabyte, and I have to send it to 256 kilobit per second bandwidth, and that means it would take 1 times 10 to the 23 kilobits over 2 to the 8 kilobits per second. It means 2 to 15 seconds, which is like 32,000 seconds, which is like 9 hours, okay? So it takes 9 hours. Okay, for one person. This was in 2007. So this is the limit for one person, okay? So first question for you guys, can we make this faster? Can you be clever, wave magic wands very high strongly and make this number lower in 2007? This is not really a trick question, huh? The answer is very simple. What is the answer? Can you make this faster? Well, if I have to send 1 gigabyte to a guy that has 256 kilobits per second download, can I make it faster? Yeah?
No.
No, yeah, that's completely right. No, for one person, that you have limit. But what about for many people? So this was 2007. Nowadays, if you make the computation, let's say I have 16 gigabyte file and I have 256 megabit per second. So this one is 4 times more, but this one is 1,000 times faster. So that makes this 256 times faster, which means 2 to the 8th. So it's only 127 seconds. Way. So today, this would only take 2 minutes, okay? So that's okay for one person, but what about many people? Now, our server, we had a server of 1 megabit per second, going to 256 kilobit per second links. So clearly the server can serve 4 clients. So assume that 1,000 people want that file. Well, after 9 hours, 4 have it. 9 more hours, 18 will have it. Another for 9 hours, you have 12 people have it. That's not very good, and even today it wouldn't be very good. After 2 minutes, 4 people have it. So the number of people you have that have it is how many times 2 minutes times 4, okay? So that's not good, okay? You can imagine that we're going to do better. You can imagine how we're going to do it, right? Quantity distribution. So basically there's unutilized resources here. We have a server, we have clients. What are the resources? Well, the server has upload, ability, bandwidth. It also has download, B. The clients have upload and download, ability, C and D. Or maybe there's no unutilized resources in this example. So if I send this and I send it to these 4 guys, where are the unutilized resources? Yeah?
The upload of the client?
The upload of the client, exactly. We're not using this uploads, okay, at all. Okay, so E is wrong, yeah? The unutilized resource, it's also the download of the server, but maybe that's not so important. It's mostly the upload of the client, okay? Okay, so now let's look a little bit more. Okay, let's slice the file into pieces. Now you can't send the file all at once, so it's nice to look at small, nice pieces. 256 kilobytes, okay? So a client with a bandwidth of 256 kilobits per second will take 8 seconds to download a piece. If the download bandwidth is 64 kilobits per second, how did people ever survive on that? I don't know, but they did. They were very happy. Even less. I remember using 1200 baud. You guys don't remember that? Okay, text typing. So 32 seconds for 64 kilobit per second. Okay, so we're looking at pieces now. So here we have my server sending to 4 clients. How long does this guy need to get his first piece? 8 seconds. Okay, and in the second scenario, here you have a second guy. How long does this guy? This guy is actually sitting behind the first guy. Upload, download. How long does this guy need to wait? Well, first he has to wait 8 seconds until this guy gets it, and then another 8 seconds, so 16 seconds. Okay? But in the second scenario, let's say all these 4 guys, instead of spreading themselves over these 4, they all attach themselves to this one. Doesn't seem to be so good because they're going to have to divide this. So how long is it going to take in the second scenario for each of these guys? You tell me. Yeah?
4 times longer for the...
4 times longer here, plus 8 seconds. So it's going to take something like 32 plus 8, 40 seconds. So that's not very good. So this is a bad choice, but this is a better choice, okay? So that's just an example to show what's called peer selection. Peer selection means, so the clients are going to connect to each other, and each client is going to connect to another client. Now we call them peers because there's no central node in this system. Huh? There's going to be no central server. They're only clients. And each peer connects to another peer. And the peer selection is very important. You see that it makes a big difference, huh? Okay? Okay, so here's another possibility. I have these 4 guys. Now I have these connections here. Okay, all of these connections. I have these 4 connections. Okay, here I download from 4 neighbors, 1, 2, 3, 4, and I upload to 3 neighbors. So the download rate is 256 kilobits, and the upload rate 192. That's already much better, huh? So are there any unutilized resources here? Well, not really so many anymore, huh? Okay. Okay, so this is something called, the first thing is peer selection. The client has to connect to the right client. There's another concept. So the choice of peers, it's not the only thing. Here's 2 examples we can compare. Even though it's possible to download at full speed, we might be forced to download slower. So for example, downloading the first piece. So here I'm sending the first piece to all of these guys. And here I'm sending piece 1, piece 2, piece 3, piece 4 to the 4 guys. Okay? So what happens? Well, as soon as each of these guys has piece 1, then that's all. They can't do anything more. But here, as soon as each of these guys has a piece, they can immediately forward it between the clients. So they don't have to stop until piece 2. So this is called piece selection. So the second scenario doesn't have this blockage. Huh? So this is called piece selection. So you have peer selection. The client selects the peer, and the file is divided into pieces, and you select the piece. So the 2 important concepts for our algorithm, content distribution, are peer selection and piece selection. Selecting the peers and selecting the pieces. And if you do it right, you will maximize the utilization. All the resources will be busy, and the download will go pretty fast, actually. Okay? That's what we want to achieve. Now, how do you achieve that? Okay? Okay, so here's a problem. Given a set of peers with known bandwidths, give a schedule listing all the connections between the peers and specifying which piece should be transferred to which peer first. So basically have some algorithm that figures out what is the best schedule. Okay, and do it optimally. In the example I'll show you can make an optimal algorithm. But that doesn't really work in practice. You have bigger heterogeneous systems, and also you can't really determine an optimal algorithm. There's many problems. So first of all, it's NP-complete. Determining an optimal schedule is an NP-complete problem, which you know what that means. So that means we don't know of any polynomial solution, and the guy who finds one will get the Turing Award, okay? But probably it's not possible. But even so, even if you do have an optimal algorithm, who will enforce it? How do you know we're actually following the algorithm? And what if a node fails? Okay? Okay, so but the basic problem is this. There's 2 ways to think about this thing. Assume global knowledge. We have some central authority orchestrating everything. Or assume no global knowledge. Okay? No machine wants to be the authority, for example. And even if it wants to be the authority, who is forcing the peers to obey it? Okay, it might not. And this is actually, in real life, it's actually much even harder than that. First of all, the bandwidth is fluctuating, and the internet not constant. Peers come and go. I turn off my machine, the peer is gone. Peers are selfish. That's a real problem. Once I have my file and it's complete, why do I need to keep staying? I just turn, why do I spend my money to help others? I just disconnect. So you download the file and run away. You have selfish peers. Okay? So the global algorithm doesn't really work. Okay? But, okay, assume we have a central peer, knows all the peers, and you make random decisions. Okay? Randomness. Okay? Let peers be connected in a random fashion, and all the peers have roughly the same number of links, and peers choose random pieces. Maybe that's already kind of nice, is it? Is it kind of a nice way? Actually, that actually is kind of nice, if you can make it work. So, the BitTorrent algorithm is a way of making this work. In a real dynamic system, we have selfish peers, where things are very dynamic, peers can come and go and fail, and it's not completely random. You can't be always random. You also have the notion of an end game, okay? It's very interesting. In the T-man, we naturally have this end game notion appear. When the algorithm nears the end of its operation, things are different, and you cannot use the same approach. It's the same thing happens here, okay? Okay, so now let me go into a little bit BitTorrent ideas. Now we'll introduce this wonderfully weird BitTorrent terminology. So BitTorrent historically is a very important algorithm, and it's still kind of the foundation of decentralized content distribution. And this is a quote from January 2005, the BitTorrent effect. Movie studios hate it, file swappers love it. Bram Cohen's blazing fast peer-to-peer software has turned the internet into a universal TiVo. For free video on demand, just click here. So Bram Cohen was the inventor of BitTorrent, and you see this thing really changed content distribution. Okay? People never saw something so amazingly fast for content distribution. So how does BitTorrent work? Well, BitTorrent has ideas coming from economics, where economics is an interesting area where the participants are selfish, okay? So actually, if you want to know more, there's a course on reasoning on a connected network. So I'm going to make an unashamed ad from this course, which says a lot about how humans on the internet, how that works. Humans are very selfish beasts with their own will, and they want to know what they want. How do you get all these weird humans working together? Well, here is the same idea in BitTorrent. So they introduce a bunch of funny terminology: seeds, leechers, tracker, torrent file, choking, unchoking, rarest first, tit for tat, Pareto efficiency. These are concepts, many of them coming from economics. Okay, so seeds. A seed is a machine that has a complete copy of the file. Usually the seeds are selfish, and there's really no reason for them to stay after they get the file. But you need at least one seed, the first seed, to stay. So you need a little bit of altruism, of unselfishness, little bit, but not so much, little bit, so that one complete copy of the file is served. Okay? So at all times, all pieces of the file must be somewhere, but not in one place. That's very smart. You only need actually one seed to be in there long enough to give one copy, but once it's done that, it can leave. And after that, you don't need to have any one node, but the 5 pieces have to be somewhere, okay? So that's very smart, okay? So even if all the other nodes are selfish, you can still download, okay? Now you have leechers. A leech in French is a sensu, yeah?
If I post a file on BitTorrent, so I post it completely, I'm the seeder, and then someone downloads it, for example, and I leave, how do they verify the file is the same than...
How they verify it's actually the same? You mean like as in authentication?
Yeah, like...
I don't know, I'm not going to talk about authentication. You can put in signatures or something to verify that the pieces are authentic pieces. So I'm not going to talk about that part of it. But yeah, if you don't trust people to give you good pieces, you have to put some mechanism for authentication. Yeah, so I'm not going to talk about that. But yeah, there's different ways of doing it. But so I'm just going to talk about how the file is distributed, despite that you have selfish seeds and that you have very dynamic kind of system. So the seeds, you only really need one, but you can have multiple seeds. So usually there's always going to be some people that are seeds, amazingly. They just leave their system on. They're not really they're kind of nice. But you don't really need very many of those. You only really need one. And the others are called leechers. A leech, sensu, is some kind of an animal in the water that sucks your blood, okay? Which are actually very nice animals. They have a bad reputation. But these are called leechers. But once the leecher has a complete file, it becomes a seed. And then you have trackers who kind of observe everything and keep track of who are the seeds and the leechers, okay? So that's the beginning. But now we get more into BitTorrent, okay? Okay, I have a file, and I want to give it to the public, so I'm a nice guy, and I don't care, I'm not making money. So I create a meta information file. Okay, the file is called Mask of Sorrow, and it's 1 gigabyte, okay? I publish this file on a tracker, and there is a web page or an email that has a link to that, okay? So the tracker knows that I have this file, okay? And it's on a web page so other people can see it to B and C. Okay. Now, I want to see the Mask of Zorro, okay? I like swashbuckling movies. So I go to the tracker's website, I send him a message, and the tracker gives me a message instead of peers. So the tracker knows some of the peers, okay? And the tracker, this is really the most important work of the tracker. It's giving me the list of peers. So I get some peers, 40, some number, not too small, not too big. But sometimes trackers do more, they can do statistics and stuff. But they really, the most important thing is they can give me peers. So I'm here, I'm H. I say, I want this file, and the tracker tells me some peers. Okay, so now we can start doing things. So I'm here, I have my 40 peers. I send a handshake message to all of the 40 peers. So I send a message, and I will get a reply. And the information in this message is very important, so it connects me into the system. Okay? Okay. Once the peers know about each other, because of the handshake, they exchange bit fields. And the bit field is just a vector, and each bit tells me whether or not I have a certain piece of the file. So it starts out with all zeros, huh? If you're seeing, it's all ones. So I send bit field to everyone, okay? And they send bit field back to me. So they know what I have, and I know what they have, okay? Of course, I start having nothing, but in general, I will have something, and they will have something. Okay, now it gets interesting. Every Lecture knows what the other peers have. Okay? Now, A and B know about each other. And so there's that bidirectional link. And there's two bits, two flags. There's a choked flag and interested flag. Choked and interested. Choked means, do I want to give pieces to B or not? So if I don't, then choked is true. So why is it called choked? And so, étranglé. So if you strangle B, then you're not giving him anything. Choked is true. But B has choked false for A, so that means B is willing to give things to A. A has an interested in false, that means it's not interested in any of the pieces from B. Okay? B, on the other hand, is willing to give to A, and B is interested in A's pieces. So that's the information. So for each peer you're connected to, you keep these two flags. So the choked flag is very important. Usually you're not going to unchoke so many nodes. Unchoking is an important thing, okay? Okay, so interested is true false based on the bit fields. If the other guy has a bit field that I don't have, then I'm interested, okay? Choked initially is true, which means initially I don't give anything. Okay? When I'm interested in another peer, and he unchokes me, then I request a piece. Okay? But how do you unchoke? So unchoking is interesting because it means you want to give pieces, but you also want to get something back. Okay? So unchoking is like peer selection. When you unchoke a peer, you've selected that one. So among the 40 or some number you know, you unchoke a small number, so that's, you select them. And then of course you do piece selection. Okay, so assume you unchoke somebody. Okay, now there's three policies. Okay, rarest first, random first, and endgame. Okay, and okay, just to make it very clear, usually you divide even a piece into sub-pieces, and you take all the sub-pieces from the same peer, but that's kind of a detail, okay? Okay, rarest first. So you know all these peers, you know the bit vectors, you choose the piece that is rarest among your peers, okay? That is the rarest one. Why is that? It reduces the effect of a selfish seed. If there's one piece that is only available in two other places, or in one other place, that's very fragile. Okay, so you're going to focus on that one, rarest first. Reducing the effect of a selfish seed also increases the usefulness, because otherwise everybody who wants that piece has to go to that one guy. But if more peers have it, then it's more usefulness for you, okay? So that's one. Okay, so rarest first is the normal kind of approach for piece selection, but in the very beginning, you don't do that. When you start, you don't do rarest first. You want to start as fast as possible. So basically, it's the fastest one. The first one that arrives is the one you use, okay? So, which is kind of random first, okay? And the other exception is at the very end. At the very end, you only have a very small number of pieces that are missing, okay? You have maybe 5 pieces that are missing, so you really focus on those, and you will also send the requests of the sub-pieces, okay, to different peers. Okay, so that's about piece selection. Now, the choking, which is the peer selection. So the basic idea is to punish selfish users. So, which is called tit for tat. So it's a typical economics thing. The algorithm has to be good for both people, okay? And so the algorithm actually tries to achieve something called Pareto efficiency. This is a concept from economics. Basically, a system is Pareto optimal if you cannot change the prices of two, or the resources of two guys, and make both of them happier. Okay? That means locally, every local connection is the best. And in certain conditions, this can actually give global optima. Everyone is going to do that. Everyone is going to have when I buy something, I'm going to buy the cheapest thing. So I'm at Pareto efficiency. Pareto optimal is a very normal thing. And that's like the motor of the economy. But you want that to lead to some kind of global optimum. So that depends on how the algorithm is designed. And the way that BitTorrent works is it has this choke-unchoke algorithm, and it depends on the download rate. Okay? Someone who is very fast, that you get things very fast, you will keep them unchoked. But someone who slows down, you will choke them. And every 10 seconds, you change the decision, and you have a maximum of 4 unchoked peers. Okay? So why these magic numbers? Well, because it works. It's somehow been optimized. So in the real system, these numbers maybe can change a little bit. So a peer has, let's say, 80 connections. 40 are initiated by the peer, 40 by others. A peer will only unchoke 4 simultaneously. And the decision about unchoking is reconsidered every 10 seconds. Okay, so you don't want to redecide all the time. So during this time, you can be sending information. 3 of the 4 are unchoked, if they're interested, based on their upload rate to me. Okay, if they are giving me things, I will give them things. Okay, this is called tit for tat. Peers who give me pieces, I will give them pieces. So it's like a positive situation. So if the peer is benefiting me, I will benefit them, and they will keep benefiting me, and then everything is very nice. Okay, so he has unchoked me, and if the upload rate is high enough, I will unchoke them up to 3. Okay, and that's not all. In order that the algorithm does not get stuck in a small set of peers, the final one is picked randomly. Okay, the 4th one, in the 40 remaining connections, it's randomly, you pick one that's not so slow, a fast guy, but you don't care if they're unchoked or not. You just pick a fast guy. And you unchoke them, and they will get a message from you, and they might say, oh, well, this is nice, I will unchoke them, and then you start a nice affair. But if they don't unchoke you, then maybe you change, okay? So you see there's kind of a positive benefit effect. I benefit you, you benefit me, okay? See how it works, Optimistic unchoking. Yeah, so if you have unused, there's some additional thing. If there's an unused connection, you can unchoke optimistically, okay? And after you finish the download, you keep uploading, but only to fast users, okay? So basically that's how it works. So you have piece selection and peer selection. Piece selection is mostly rarest first, except in the very beginning and the very end. Okay? And in peer selection, you have 2 things. The initial construction of the list, and then the choosing which peer to upload to, is the unchoking. Okay? It's choice based on which peer can give me pieces faster, the speed, but also it's a positive thing. If they unchoke me, I will unchoke them. Okay? That's called tit for tat. I'm not sure there was a slide on tit for tat. Tit for tat means that if two agents interact, you assume the other guy is honest. And you assume he's good, and you give him something first, without expecting anything in return. And then, if the guy gives you something back, then you have a positive exchanging. Okay? Now, if the guy cheats, give him something, and he doesn't give you anything in return, he cheats, then you will break the connection, you will not continue, but only for one step. You don't have a long memory of that, okay? Tit for tat means that if I hit somebody, he hits you back, but then he forgets. You only get one punishment for a bad action. So if the guy is later honest, then it will be honest again. So you basically punish dishonesty, but only shortly, okay? One time. Okay, there's some other technicalities. Firewalls, network address translation. So BitTorrent has some mechanisms to escape that, which I'm not going to talk about. Stun, tunneling, and so on, but I want to talk about that. Okay, so I think we're a little bit early, but that's okay. So is that clear for everyone, how BitTorrent works? So the choking, unchoking, is what's called a tit for tat scheme, where you unchoke someone first, and if they unchoke you, then you start exchanging information. But if they stop, then you will stop. But you will start again later. So basically, you create this thing which is beneficial for both, and if it's not beneficial for one, the other will stop. Okay? So that means both of them are selfish, and the selfishness will keep them going. Okay? Tit for tat. So that's how economics also works. Huh? Every agent, every human agent, I am not working to improve society. I'm working to improve the situation of Peter Van Roy. Maybe I'm idealist, but the set of idealists is very small, and even then they're not really that idealist. But the society has to be designed, so when I am improving myself, I'm also improving society, okay? So for some reason, I like to teach, so I'm teaching. That helps me, I feel good about it, but it also helps you guys, okay? So that's how economics works. You basically use the selfishness to keep the thing moving. And BitTorrent was really one of the first internet peer-to-peer systems that was able to do that. So you see, it's kind of a version of gossip. It has peer selection, and it has this exchange, but with this extra thing, the choking, unchoking. You see the new thing, the incentive? Okay, I'm done a little early, but I don't think that's a problem. So I think we're good. So thank you very much. I think I stopped here.